So good morning, everybody, and welcome for this new seminar. Today we will have the talk by Dr. Milagros Colazo from Astronomical Observatory Institute in the Mickiewicz University in Boston, in Poland. She will talk about phase curve fitting in the context of large-scale photometric surveys. Dr. Álvaro Álvarez Candal will introduce her as he invites Milagros to talk.
Milagros finished her PhD in the Universidad Nacional de Córdoba in Argentina in 2023 under the supervision of Dr. René Lupar. And she started then her postdoc in Poznan, in Poland, under the supervision of Dagmara Mickiewicz and pardon me, Przemysław Batsak. Where she's working now for slightly over a year already, and she's been here for the last 10 days collaborating with Renee and myself on this fascinating world of phase curves and asteroids.
Hello, everyone. Thank you for the introduction. As they say, I will talk about my current work in Poznan at the Mickiewicz University. The title of the presentation is Asteroid Phase Curves and the Phase Coloring Effect, Insights from Large-Scale Photometric Surveys. I will talk about a little bit also about some of the previous work that we done. So, first of all, a little introduction about my research focus. So I studied asteroid phase curves. As you know, the asteroid's brightness changes due to rotation. I think this one is the most famous one. And as the asteroid rotates, one can obtain the light curves of the object. But the brightness of the asteroid also changes as it moves around the sun. So we can obtain there the phase curve of the asteroid. Yes. Where in general, okay, the brightness is higher, so the magnitude is lower for small phase angles, and for larger phase angles, we can see a decrease in the magnitude of the asteroid. So this is my object of study. Okay. So what have we done in our group? We published last year a paper where Villaver was the first author, phase curve wavelength dependency as revealed by shape and geometry corrected asteroid phase curves. So the data collection for this work were some dense differential ground-based observations obtained on our observatory. And with that data, we model the asteroids focusing on the sidereal rotational period and spin axis. And we combine that dense, that dense data with some sparse data from Atlas catalog. That data was used to calculate the photometric phase function with the it's okay. With the parameters obtained with the dense data. And the selection criteria for this work were 35 asteroids with well-defined models, accurate period, and pole coordinate based on photometric data from 11 previous studies. You can check this paper out using the QR. Well, here you can see the summary of the method, which is really, really complicated. It has to do with the inverse problem formulation from Winonen and collaborators from 2022. Of course, it was adapted to a supercomputer, the Poznan Supercomputing Center. So for the first part, as I said before, one has to solve the spin and shape parameters using the ground-based photometry. And for the second part, using the initial solutions to sample both photometrics parameters G1 and G2 with the spin and shape parameters through MCMC. Yes, so here you can see the MCMC for the G1 and G2 parameters using two pole solutions, yeah, and with the cross you can see the mean value and the standard deviation. So with that method, we obtained the phase curves of the 35 asteroids. Also, we performed some phase coloring analysis. Yeah, so here you can see the phase curves in cyan and orange filter for, in this case, for Clitia, the two pole solutions. The shaded areas are the 1 sigma envelope, yeah. And here you can see the slopes, the phase color, the spectral slopes. So here we obtain this, the color slope, sorry, we obtain this by doing a first derivative in the phase functions. And as you can see, we can see the reddening here for both pole solutions. But here, the shaded area, which is the 1 sigma uncertainty, can also suggest bluening. Yes, so we are really interested in this behavior of the color slope, and we are trying to know if one can see this effect without doubt. Yes, because here actually we can see reddening, but it could also be bluening. And well, in this work, we analyze the photometric properties of 35 asteroids using the 10 grounds base data and the sparse atlas data. And also with the analysis of the opposition effect, the phase curves for small phase angles, we can identify preferred rotational poles, yes? Because, for example, this, we can say that this model is bad because the opposition effect is not so realistic. But, for example, with this pole solution, the opposition effect is more reliable. And this and Marciniak and collaborators in 2008, they also identified this second solution as the preferred. So our results are consistent with this. So this was like the introduction for our last paper that you can see here the archive, but I hope that we will have it published in Icarus within a few days. So this title is Asteroid Phase Curves and Reddening Effect using Atlas Survey data. Yes. So for this paper, we use the AG1G2 phase function developed by Munonen and collaborators, but in a multi-opposition fitting approach. So we converted the magnitude to flats, and we divide it into the different filters. In this case, we are using Atlas, so it will be cyan and orange. And the function that we are fitting is this one, the AG1G2. But we are splitting the data into the different apparitions. Yes, so for doing that, we use the solar elongation information downloaded from the GPL Horizon system. And then for each filter, the data from various oppositions are fitted simultaneously. So we obtain one G1 and G2 parameter for the whole points, but for each apparition, we will obtain absolute magnitude. Yeah. So here you can see that we split into the different apparitions. There will be only one G1 and G2 for all the points, but each apparition will have a distinct absolute magnitude. So we are using, I think that I didn't say, the version 2 of the Atlas Solar System, which was released last year in May. Then we have to do an outlier rejection, which is quite slow and manual, and we are working now with another approach. The first step, of course, was to remove the points that lie very far from the mean value of the distribution of the points. So, for example, these points here. For the second step, we feed a linear exponential phase function to this data. Then we compute the root mean square residual, and we remove all the measurements that differ from the fitting phase function by more than 1.5 RMS. This approach was used before by Hanus and Durek and collaborators. And there you can see these green points are discarded during this step. And for the final step, we apply additional rejection criterion using the reporting maximum amplitude of each asteroid Lie curve of each asteroid in the Lie curve database. And in the case the asteroid didn't have maximum amplitude reported in that catalog, we assign it a value of 1. So you can see here in this histogram, these are the maximum amplitude of the Lie curve database. And 95% of the sample have maximum amplitude less than 1 magnitude. So I think this criteria is fine. And then we calculated the mean magnitude and reject the points that deviate from the mean by more than the amplitude of the asteroid. So yeah, this is a very complicated outlier rejection steps. But well, finally, we obtained the phase curves for more than 300,000 objects for the orange filter and 280,000 asteroids in the cyan filter. But here, maybe, okay. For the, with accuracy better than 50% of the parameter value, we have quite a smaller number for orange and for cyan. So this is the histogram of the absolute magnitudes for all the asteroids that fall within these Pentila conditions, you know, that the G1s and G2 are between 0 and 1. And here you can see the G1 and G2.
Sorry.
It's okay. The G1 and G2 kernel density estimations, yes, for the orange and the cyan samples. And here you can see the histograms of the uncertainties. So we notice here that the G1 parameter always has larger uncertainties than the G2 parameter. And this is also replicated in other databases, as I will show you later. Well, we analyze also these results for different taxonomic types, cross-referencing our database with the DMIO and collaborators database for taxonomy. And we use an analysis that follows the approach of Malki and collaborators 2021, but applied to this newest release of the Atlas catalog. This is the number of the almost 7,500 asteroids in orange for the different taxonomic types. As you can see here, for the dark albedo objects, we have more larger values of G1 than for the low albedo asteroids than for the high albedo asteroids, as expected, of course. And here are the results for the cyan filters, where, of course, we also have less objects and more or less the same behavior. Yes, like we can find larger values of G1 for the dark albedo object than for the high albedo. And here is a summary of each taxonomic type in each filter, orange and cyan, in the G1 and G2 space. So as you can see, the high albedo objects are in the left corner, having lower G1 values and higher G2 values, while the darker objects have larger G1 values and lower G2 values. But if we compare these results with another works, for example, the one from Mickiewicz, something that we notice is that our G1 and G2 values are not as extreme as theirs, because they have G1 values really close to 1. But we notice also that that could happen when you use a restricted least square, a constrained least square fit, and we are not doing that because sometimes if the fit fails, it goes to those extreme values. We are not sure if they are correct. Well, then we also perform a two-dimensional Kolmogorov-Smirnov test, for the different taxonomic types. Yes, so for the upper triangle, we have the comparison of G1 and G2 distributions for filter. And for the in the lower triangle, we have the comparison between the G1 and G2 parameters for the orange filters. Yes, so we use a 95% confidence level. We will reject the null hypothesis. The null hypothesis being that the distributions are drawn from the same population, in favor of the alternative hypothesis that they are statistically different if the p-value is less than 0.05. Yes, so for our sample, we didn't reject the null hypothesis in 11% of the orange sample and 31% of the cyan sample. This was also found in Milagros' paper, a similar trend. There is one p-value exactly at the 0.05 threshold, which corresponds to the LX pair. No, is the BX. Well, is a typo? Yeah, okay. The BX is the only one that is in the limit. The X complex is quite strange, but I guess that these two should be rejected. So there is two pairs of values here, the AQ and BA pairs in the cyan filter that are quite, AB and QB that are really close to 1, which is expected because those taxonomy types have similar values of albedo. And well, we also analyze the G1 and G2 distributions for the asteroids families. Here are some of them. The family identification was performed with the asteroid dynamic site. And again, we put here a summary of the centroids of these distributions. Again, the G1 and G2 values are not as extreme as other publications, but again, kind of the more dark families are in the right lower corner, while the families with high albedos are in the upper left corner. Well, then we analyze the phase coloring. The phase reddening effect causes an increase in spectral slope as the phase angle increases. But Álvaro proposed the term phase coloring based on evidence suggesting that some objects tend to lower. And to evaluate this wavelength dependency, we compare the pair distributions of G1, G2 in orange and G1 and G2 in cyan within same taxonomic type. The former plot and analysis was between different taxa, but here we are analyzing the G1 and G2 distribution in the same filter for the same taxonomic type to evaluate this wavelength dependency. We performed here the two-dimensional Kolmogorov-Smirnov test, and we observed statistical significant differences in all countries except for the A complex. And we also performed the one-dimensional Kolmogorov-Smirnov test in G1 and G2 values. And as you can see, the G2 parameter is the one that exhibits most statistically significant differences. And for example, we can see here that for the A type, neither the G1, neither the G2 are statistically different. So the two-dimensional Kolmogorov-Smirnov test yields the same conclusion. Yes. Then, well, we also present the distribution of objects in the G1 and G2 space, but restricted to the most numerous C and S types asteroids. This is the best sample with the uncertainty less than 50% of the parameter. So here you can see the G1 and G2 distribution in orange filter and the G1 and G2 distribution for the cyan filters. And we can see here also that the S complex is more towards the upper left, and the dark C type objects are more in the right lower corner. And here we also have the histograms of the G1 and G2 distributions in orange and in filter for the C and S asteroids. And as you can see here, the mean G value, the G1 value for the S types in the orange filter is lower than the mean G value, the mean G1 value in the cyan filter. Yeah. Although the mean G1 value for the C types asteroids is quite similar in both plots. Yes, and this was also noticed by Bilever and collaborators in 2024, and they suggest that this may be attributed to the tendency of higher albedo asteroids to present flatter phase curves. And again, well, we computed the color slopes as the difference of the first derivative of the photometric phase function, AG1, G2, with respect to the phase angle in the orange and cyan filters, following what Bilever and collaborators did. And in our sample, 58 asteroids exhibit reddening effect, I mean this, and 55 a bluening effect, I mean this, for the small phase angles. Yes, so here you can see the color slopes. These lines here that are not so obvious are the minimum phase angle in orange and in cyan. So it is true that in some cases, for example, this one, this is actually an interpolation. We don't have data here. But for other objects, well, it is better. And in general, for large phase angles, all of them present reddening. Of course, there are some cases where you can see bluening, but for example, in this case, actually, it's almost zero, is the effect there. Well, as I said, our method is quite simple because we split it into apparitions and just perform this square fitting. So we compare our method with other methods presented in the literature. For example, the one of Bilever. They use, as I said, ground-based data with sparse data combined. It is a very expensive method. It requires about a month of computational time and in supercomputation adaptations, of course. Our approach is simpler, but excludes some effects like the rotational correction that can be important, for example, for near-Earth asteroids. Our method is designed for scalability when working with hundreds of thousands of objects, and it took only 1 minute to perform the outlier rejection and the phase curve fitting for the sample of 35 asteroids that Bilever used. Yes, so it took us 1 minute, while for the other method it took months. And as you can see here, this is the comparison of the G1 and G2 parameters with the different poll solutions, yes, between our work and Bilever work. And the results are similar. Again, the G1 parameter is always more problematic, but for the G2 parameter looks more or less okay. The darker points are the one where the uncertainty ranges overlap, and the yellow points are the one where that doesn't happen. And okay. Yes, I think, okay, yes. The difference in G1 values are particularly noticeable for objects with sparse data near the opposition, because the G1 value is pretty, how you say this? Influenced by the number of points during in the opposition effect region. We also compare the method with the one that Gary proposed, Bernard Gary last year, which is quite new. They propose a phase function model that considers the variability between apparitions and adds a term for asteroid orientation, obliqueness, and equatorial coordinates. Again, the comparison with Benoit is in this row. The results looks similar also. We suggest that separating by apparitions or adding the orientation term is comparable. What we can see is that their absolute magnitudes are slightly brighter than ours, but this is likely due to the biases in the data, which our method cannot take into account because we are not correcting for spin and shape. And as I said, this is important for near-Earth objects, and we check there the delta, the difference between apparitions in H. The maximum one is the average, sorry, is 0.22. And we also compare our method with Álvaro's method. He used some Monte Carlo simulations and Bayesian inference. It compares the uncertainties in magnitude and rotational variations. And here are the comparison with Álvaro. And again, the results are consistent with ours. The test that we did took 32 minutes for Álvaro's approach using 1,000 Monte Carlo iterations. Again, ours took 1 minute. And again, the G1 parameter is the one that is causing more problems, but for the H and G2 parameter, everything looks quite good. So, well, the highlight of this paper is that we determine the phase curve for more than 300,000 asteroids. We analyze the wavelength dependence using the two-dimensional Kolmogorov-Smirnov tests, showing difference between the phase curves in the origin and filters across all the taxonomic types except for the A class. I have to say that the A class is the one that has the less number of objects, so probably we still need to be pay attention to that. Then we analyze phase coloring. Yes, the phase reddening was observed in a greater proportion of asteroids at large phase angles, while both the reddening and bluening was observed at smaller phase angles below 5 degrees. Then we analyze the uncertainty patterns for the parameters. The G2 value shows lower uncertainty than the G1. In the paper, you can see also some simulations that we performed, confirming that G2 is more stable across different phase angles and distributions. We compare our method with Alvarez-Gandal method, the Bilever and Gary and collaborators. And this is really important. Our algorithm is scalable and adaptable to various datasets, including also the LSST data. We perform these fittings in the data preview 0.3, and we are also working now with Julien and Benoit to include this method in the Think broker. So here you can see the LSST application. Yes, here are the GRI-SIT phase curves. Yes, you can, well, I don't know if you can see, but there are different colors here of the point that corresponds to the different apparitions. And here you can say just a small sample of the GPO3, G1, G2 parameters for each filter 2. And here you can see the uncertainties of the G1 and G2 parameters. And again, the G2 parameter always presents smaller uncertainty values than the G1. Okay, so now I will do some announcements because this year we will host the LSST Europe in Poznan. We have the registration and abstract submission open if you want to apply. So we hope to see you there. And next year we will also host the ACM. So we are starting to organize this amazing congress. This is our flyer, and the comments are scans of all photographic plates, some from our observatory. And that's all. Thank you for listening.
Thank you, Milagros. I'm sorry for this.
No, it's okay.
The briefing is installed. So, okay, the talk is open for questions. Any question? Olga.
Yeah, well, it's impressive the amount of data that you can manage. But now I'd like to know how this reddening or bluing relates to the properties of the asteroids. Do you have any link to the properties or?
Well, I think that's the question. And now we are performing with Alvaro some spectrum observations, so we can study that in more detail. Yes.
Okay, and also related with the G1, G2 parameter, I am not familiarized with that. Do they also link to any properties of the asteroid, or that is what you are looking for with this large?
No, yes, of course. I mean, we expect, as I said, that we expect that the higher albedo objects have higher G2 values and lower G1 values, and that the dark objects have larger G1 values and lower G2 values. Yeah. But I think that in this type of works where we work with very large databases, we want to see the trends and then go and study those that got our attention like deeply, or even if we see some outlier in the trends, study some objects in particular. Just gives you this large database gives you the insights for deeper studies.
Questions?
How are the simulations for the LST done? How did they make these magnitudes? What did they use?
For the LSST GPO3,
Yeah.
I'm not sure now how they did the simulations. I think that I mean they have some real asteroids, but they also injected like invented ones. But I'm not sure now how they did it.
Okay. I guess if they are simulating at different phase angles, they are injecting in their simulations the phase curves at some point. So you are recovering that after you just recover whatever you fed the simulation.
Yeah, I mean the thing with the GPO3 is that we expect that the real data release we have the same structure, like the CSV or whatever structure, like the table structure will be the same. So that the thing that we were doing is test if our algorithm can be applied to that database. Of course, we know that they are simulated data, and it can happen. It was just a test about the application of our algorithm.
You're using LSST, or you will use LSST data. The affiliation is personal for you, or?
No, the Poland.
It's Poland, the
Poland,
country,
yeah,
not the.
Every institution I guess is involved in the LSST, yes.
We need to join this.
Yeah, the telescope is already taking images. So
Okay, more questions? Someone online want to do some questions? No? Okay.
okay, thank you.
Milagros, for this.
No tiene ningún directo propiedades físicas.
Ah, pero esto, estoy grabando acá, acércate.
Para ver.